So hi everyone. So last time we started to talk about explicit construction of expander graphs. We only spent like 5 minutes on that topic, but let me just redo it because it was supposed to be no new material and it was already playing with the line there. So in today's week we are going to present an explicit construction of expander graphs, not Ramanujan, but quite somewhat close, depending on what close means for you. And if time permits, and I think it will, we'll actually see or start to talk about Rangel's theorem, SL equals L, which is like a big thing, which we'll talk about. Okay. So the nature of this construction is combinatorial. You will see exactly what I mean. And someone asks, rightfully, like if we have like amazing expanders from 40 years ago, why do we need another construction which doesn't even match the bound that we have? So really the second part of maybe today or next week, Rangel's theorem, but also other results, kind of demonstrates the fact that the combinatorial construction that you can play with have additional advantages rather than just allow us to construct graphs. They allow us to do more things because they are really kind of dynamic. You'll see. Okay, so let me just redo anything we did. So last time we talked about the fact that we will actually, it will be more convenient for us to work with a somewhat more subtle, slightly more refined, maybe, encoding of a graph rather than just looking at the adjacency metrics. And to that end, we said that, given an undirected graph G, we say that it is labeled. It's not really a property of the graph. Every graph can be labeled, but we say that it is labeled. Someone did something to it. If you have the vertices, so maybe this is one vertex, and all graphs will be D-regular. So we say that it is labeled if every vertex kind of label the outgoing edges. It's undirected, but he thinks of them as kind of ongoing edges from 1 to D in a bijective way, right? And what is important to know that they don't need, like the two end vertices of an edge don't need to agree on the label. Not necessarily. I mean, maybe V consider U as his third neighbor and you consider V as his second. And of course you can always do that. I mean, since you don't require consistency, just if there is an order on the vertices, you can just use that, the induced order on the neighbors. But it will be more convenient to work like that. Like, who is my ith neighbor and so forth. So that's labeled graphs. And let me just remind you, actually talked about it in the first lecture, what is explicit? I mean, we want to construct an explicit graph. So what do I mean by that? So again, a graph on n vertices, undirected, they all will be undirected graphs on n vertices, and may vary. But we say that it is weakly explicit if you can generate the entire graph, say the entire adjacency matrix or a function like that for every vertex, in time which is polynomial in the output size, which is poly n. That sounds like, the obvious definition in a way. Exponential in n is easy. I mean, if you allow yourself exponential time or maybe slightly larger, like n to the n, you can go over all graphs and do things like that. So polynomial time is certainly non-trivial. That's called explicit, but you see we kind of think of it as somewhat explicit because I called it weakly explicit. And the reason is that, in some cases, like in error reduction that we saw last time, the graph size is actually exponential in the problem size. And so you want a graph which you can access locally. So the vertices are comparable in size to the problem, not the graph itself. So, that's sometimes enough and sometimes it's not enough. And okay, so the stronger definition called strongly explicit is for a labeled graph is exactly what you would think, given a vertex and a number between 1 and D, say the graph is D-regular. If not, it's a number between 1 and n or whatever. What you want is you want a function that produces the identity of this vertex, right? Who is my ith neighbor? in time, which is polynomial in the problem, which now is the size of the vertices, really. And I, but I is smaller than the encoding of the vertices, right? Because if you have a graph on n vertices, you can encode the identity of V with log n bits. You kind of go into the complexity realm here, so you have to talk about bits. And this is log d bits, but it's always smaller than log n. So you want in poly log n time to produce U. Right? In particular, if you have that, you can construct the entire graph in time which is almost linear in the graph size, because you can go over all vertices. But it's stronger than that. You can locally access the graph. Okay. Here there is some subtlety, it doesn't mind. I don't care. If the graph is not regular and you're given a number which is beyond the degree, you should maybe output a boat or something, but it's a nitpicky a little bit. Okay. And so this is kind of where we start more or less. So the construction that we will see today is actually composed of three like mini operations that by themselves have weaknesses and advantages, and somehow combining them will allow us to construct a graph with the desired properties. So we'll have three operations. I don't know if it's, we'll have squaring, which is really trivial and easy, tensoring, which is almost as trivial and easy, but not really, and the zigzag product, which is like the main, player here. So these three operations, which we will analyze separately, together, if you are clever enough, kind of use them in the right way, can give you a construction of an expander, as we'll see. So let me start by talking about the squaring. It's like a one-slide thing. Tensoring is more delicate. Maybe you're familiar with that from other courses. It's like tensoring is a very natural operators or matrices. And the zigzag product, which you probably have. How many of you have seen it? I know one person that has like a PhD on this essentially here.
Talk about it in the previous section?
The zigzag? Yes, so in the last 5 minutes, or maybe in the last lecture, we talked about squaring a little bit.
I saw this in the slideshow somewhere.
I gave another course also, but like 2 years ago, 2020. Yeah. No, we talked about like the last 5 minutes of the last lecture was about this. Right? So it's really kind of a repetition here. But it hit me that I shouldn't have done it, because it should have been I mean, this is definitely new material, so I cannot. Okay, so having in mind that we need to understand these three operations, let's consider them separately, starting with squaring. It's a very simple operation, just to warm up, but we really need it. So if you have an undirected graph on n vertices, here you don't really care about what n is, but it's the regular. So the square of the graph is what you would think. It's this, for example, depending of what you're used to. If you are used to a kind of a combinatorial perspective, it means that you take like 2 steps rather than 1 step in a random walk or whatever. If you think about the adjacency matrix, which again, everything is equivalent, you're just going to square the adjacency matrix and look at the graph that corresponds to this new operator and so forth. But let me just do it from scratch. So the square of a graph is another graph on the same vertex set, but the edge set will be different. And what's going to happen is that the neighbor, right, each neighbor of a vertex in V was kind of labeled between 1 and D. In G squared, you're going to have D squared neighbors. Maybe some of them will be the same, but D squared neighbors. And it will be convenient to not denote the neighbor number by a number from 1 to D squared, but rather by a pair in D squared. And we do it in such a way that, what is the ijth, right? Because that's the neighbor number. What is the ijth neighbor of some vertex? So if you start from a vertex V, again, it's the same vertex set as in G. So it doesn't really matter if you think of it as a vertex in G or G squared. Then, so the ijth neighbor of V is going to be as follows. So first of all, you're going to look at G, and you're going to ask who is the ith neighbor of V in G. So this is in G. So you're going to arrive to some middle vertex U. And then you're going to ask again in G, who is the jth neighbor of U, you're going to get to W, and that's the ith jth neighbor of V. Okay. It's very kind of natural, but if you think about it from a vertex perspective, let's kind of stay on this picture a little bit, and I think that's where we stopped last time. Then, the neighbors of a vertex, so I'm looking at G here, this is G, the neighbors of a vertex are, some D vertices here, and if you think about it, due to that vertex, you are going to have an edge between every two vertices here, including themselves, right? Because of that vertex, that's the friend that everyone knows in this party, then these two are going to be connected because, like that. And every two are going to be connected, and also the vertex with itself, because going back and forth is perfectly valid, and it essentially generates a self-loop in G squared at that vertex. And the self-loops, there is only one right way of thinking of it. It's a degree 1, not a degree 2 thing, right? You could imagine maybe I can go from here to here, but it doesn't work this way. It shouldn't. It will kind of destroy the relation with spectral graph. You should think of it as one. Right. So as the number, but I count each once, not twice. But you're saying maybe if there was already, or
no, like the one.
Yeah.
It was like four.
Right. Yeah. D. Yes. And this. Right, but not 2D.
No.
Yeah.
It makes sense, like you think about like the identity.
Exactly. That's the reason, really, because I want to keep spectral graph theory in the picture. So if I have any kind of ambiguity of what should I define, I'm looking at the spectral graph theory and see what happens when you square the matrix and I see a D and not a 2D, and I'm happy. That's really the reason. But I saw some books where they are on graph theory, not on spectral graph theory, and they count this as 2. Okay, so I don't know. I don't want to name names here, but it's weird. They have a discussion. They know that there are other people, like 99% of the world. There are many things like that. Of Polish notation, for example, you heard about it? So we write like that, but at some point in time in Poland, people wrote like that. And there is a computer, like a calculator, that you write X, F. Right. It's right. It's like a kind of a lambda calculus thing, but right. I don't know. Actually, as a Hebrew speaker, you might have actually feel more comfortable like that, right? But anyhow, I don't know. But we don't do that. So there are, in parallel worlds where things are behaved differently. Okay. So this is squaring, and obviously, I think, if you look at the adjacency matrix of the square of a graph, it's really just the square of the adjacency matrix of the original graph. And here also you can see that there is like a D on the diagonal if the graph is irregular. And because everything is regular, otherwise you should be slightly more careful, the random walk matrix also behaves like that. And I just remind you that for the irregular graphs, the random walk matrix is really just nothing more than the scalar normalization of the adjacency matrix. In general, you have to do something more complicated, but that's what it is. And of course, the square doesn't mind. So you're going to get from here 1 over d squared, and indeed, this square is the degree of this graph. So it kind of fits perfectly. So just dividing this by d squared, everything works out nicely. And the message here, but you know that, I guess, is that a random step on g squared is essentially a length 2 random walk on g. Because you pick a vertex at random, the same vertex set, and then you pick 2 neighbors, which is to determine where you're going, which is exactly a length 2 random walk in G. Again, the same vertex set. Otherwise, it wouldn't have made sense to say that either. Okay. So because of that, we know that omega, which let me remind you in case, you should know that like by heart at this point, omega of a graph is the maximum between omega 2 of the graph and omega n in absolute value. Let's put absolute value here as well, even though I don't need it really. Right, so omega 1 is like 1. All the omegas are, if you prefer the lambdas, are lambdas over d. So these are all normalized. Everything is between -1 and 1. So in absolute value, it's between 0 and 1. And you want omega to be small. That's what you want. Right. Yeah, good. Yes, you're right. So if you square, anyhow, what happens when you square an operator? All the eigenvalues square. So there is no even a reason to talk about absolute values anymore if you do that. But then we'll do something else also. And so in general, you don't know if that's the last operation. But in any case, omega of g squared is really omega of g squared, because the square of these two are going to be the competitives of who is the omega of this thing. It could be that actually, this one, omega n, was a negative thing in G, but its omega was in absolute value larger. And now when you take the square, he is the one that actually becomes omega, like in a bipartite graph. If you have a bipartite graph, then omega n is a -1. And when you square, you get, what do you get? 1. And so what do you know about the graph, right? If you take a disconnected, right? Unless I'm completely mistaken, because you cannot go from those vertex to those. You need an odd number of steps. So if you are aligning only even steps, you can do it. So in a bipartite graph, omega n starts as -1. Remember, that's the equivalence actually to bipartite test. We didn't prove it, but I just said that. When you square that -1 becomes a 1, and we know that happens if and only if the graph is disconnected, which corresponds indeed to the two. Yes. Right, good. But in undirected graphs, only 2 is like the possible cycle length. So in directed graphs, you could have like, and you would have like other, say, roots of unity, for example, as eigenvalues, and then things are more complicated, but not in undirected graphs, because all the eigenvalues are real. Anyhow, it's a side remark. You don't need to worry about directed graphs in this course. Okay. So that's a good thing. I mean, what I'm trying to say is that we have a very simple way of reducing omega. Just square the graph. It doesn't come without a cost. You square the degree also, right? But it seems like you gain nothing. Actually, in a sense, you lost something. But at least omega becomes smaller. There is a way of making omega smaller. So that's what squaring is doing for us. So maybe there is a picture here. We'll see it in a second, or in a couple of minutes. So squaring allows us to reduce omega, but increases the degree. And it, by the way, doesn't affect the number of vertices at all.